Hello everybody. In this video we are going to talk about a concept in calculus called continuity. Continuity in non-math senses can mean a sense of continuing or going on forever. And in math, unfortunately, that is not really what that means. You want to think of continuity as connectedness in mathematics. So there are no breaks, there are no holes, there's no interruptions in the graph, and it's all in one nice connected piece. Okay, so I'm going to share with you what I'll call a continuity test, or basically the three conditions for a function to be continuous at a particular point. And then we'll look at what those conditions look like graphically. Okay, so for symbols, then we'll take a look at some pictures and see how they relate to each other. Okay, so here is the continuity test. We say that a function, f of x, is continuous at a point x equals something. So I'll just use x equals c. If and only if the following three conditions, all of them, are true. Okay, so first of all, we can't have a hole or a vertical asymptote in the graph. In other words, you have to be able to plug in that x value into the function. So the way to say that mathematically in symbols is to say f of c is defined. You don't get 0 over 0 when you plug in the number. You don't get something over 0, or just you get a number that makes sense. There's a point on the graph. Okay, so that's what this is saying. So this kind of says that, well, in order to be continuous, what we have to be true, for one thing, is at least there has to be no vertical asymptotes and no holes at that particular x value. The second thing that we need is, this isn't, the first thing isn't enough because we can have a jump in the graph where you can plug in the value, the x value, but there's a point where it jumps down to another point right there. So we've seen this with piecewise functions so far. And so the second condition that we need is that the limit from the left-hand side as you approach c has to be equal to the limit from the right-hand side as you approach c. So this says that in order to be continuous, we can't have any jumps or breaks in the graph. That should make sense, right? If we have a sense of connectedness, there can't be any point where we have to, like, if we were sketching, is pick up our pencil and start somewhere else. We have to be able to draw it in one line, basically, without picking up our pen or pencil. Okay, so what this says is we can't have any jumps or breaks in the graph if we're going to be continuous there at the point c, x equals c. Okay, but that still isn't enough. There's still one more thing that we need. And that is that as you are approaching c, the limit where it looks like it's heading towards has to actually be what you get when you plug in the x value of c. Okay, so the limit as x approaches c of f of x, it has to actually go where it looks like it's going. So this has to equal f of c. I don't really have a word for what this looks like. You'll see a picture in just a moment. I don't know what to call this, so maybe you can come up with something and let me know. All right, so let's look at these three different graphs here. Find any points of discontinuity, and then state which part of the continuity test that is not satisfied. So which one of the three parts of the test above here are not met in these graphs. There could be more than one. But we're going to go through all three. Okay, so the first graph has this asymptote at x equals c. So that means already this graph is like split up into two different parts, right? We've got this part here that's nice and continuous on its own, but then once we start to include C, there's a break in the graph. Then this part is nice and continuous on its own as well. So it looks like the only issue, the only point that's an issue here for violating the connectedness that we need is right at x equals C. Okay, so the way we would say that is we have a discontinuity at x equals C. Okay, another way that we could phrase this is we could say or continuous on everywhere else. So it's continuous from negative infinity up to C, and then from C to infinity. So this would be another equivalent way that you could write this. So let's go through each of the conditions and see which one is met. So the first one says f of C is defined. So is that true in this case? I don't think so, because we have a vertical asymptote there. So right away, we are failing that first condition. So I would say 1 is violated. F of C is not defined. So that's the reason why we have this discontinuity there. And we don't have to check the other two, because in order to be continuous at a point, we need all three, right? All three of these things need to hold. So condition 1 automatically is not satisfied. Okay, example 2, this graph in the middle. We have a part of the graph that is just nice and continuous here until when we get to C. If I'm sketching the graph from left to right, I've got to pick up my pencil in order to start the graph again and keep on going. So wherever that happened, and I've got it nice and labeled here for us, is at C, right? So this is another point of discontinuity. So we say discontinuity at x equals C. Or continuous on the interval from negative infinity up to C, that's this part. Then C is the problem where we have a discontinuity, so we'll remove that. And then from C on, this part is continuous. Okay, so you could describe it that way as well. In this case, if we go through all of the conditions, here f of C, we can actually plug C into the function, right? This filled in circle here, that means that that is where we read off the function value. So here there's no problem with number 1. So f of C is defined. Okay, that one has no issues with that, so that one is good. So we move on and we see what's happening with the rest. Number 2, is the limit from the left-hand side at C equal to the limit from the right-hand side at C? I think this is the one that is a problem, right? As we're going towards C from the left, remember we're coming from the right, but coming from the left, moving to the right when we're looking at the left-sided limit. That's heading towards this point here, this y value. But from the right, as we approach C, that's heading towards this point here, this y value. And these aren't the same. So the limit from the left and the right aren't the same, right? So actually number 2 here is violated. So the limit as x approaches C from the left of f of x is not equal to the limit as x approaches C from the right of f of x. And this is the one that this function doesn't satisfy at x equals C. Okay, in our last picture here, I hope it's clear to see that we have a discontinuity at x equals C again. So let's note that. Right, there's a point here at x equals C where we have to pick up our pen or pencil as we're drawing this graph. Right, it's not in one connected piece the whole way. This part is nice and connected. Then we have almost a separate part here. And then we have this third separate part over here. So there's almost like 3 pieces to the graph. Okay, and right at C is the problematic place. Okay, so let's go ahead and go through each of the conditions. So here, number 1, is f of C defined? And I think yes, right, because we have this filled in circle here. So this would indicate that when we actually get to C, when we plug it into the function, we're going to take whatever this y value is for that dot there. Okay, so f of C is defined. Okay, so number 1, we pass. We move on to number 2. Is the limit from the left-hand side at C equal to the limit from the right-hand side at C? Well, if we're going towards C from the left-hand side, remember the limit doesn't see the point, so we just cover up actually what's happening at C. And if we go towards C from the left, we're heading towards, like right around here, that hole. And as we go towards C from the right, we're heading towards the same place. So these actually are going to, the limits will meet. Not really, but they will match, I guess is a better way to say that. They will have the same value. So here we have condition 2 is also satisfied. Okay, the limit from the left-hand side is actually equal to the limit from the right-hand side. Okay, but the one that's violated is this third one here. Okay, so as you approach C, where we are looking like we're heading towards is at this hole, but that's not equal to the function value, which is down here. So the limit is not the same as the function value. We would need that hole to be filled in by the point in order to have continuity. That's what part 3 means. Okay, we would need the limit where it looks like we're heading towards be actually equal to the point that you get when you plug in that x value. Okay, so if this, this hole were just kind of moved up to here and filled that in, we would have number 3 here be good, but we don't have that case. So in here we have the limit as x approaches C of f of x is not equal to f of C. So that's what that one kind of looks like graphically. Okay, so we want to be familiar and comfortable with using this notation with limits to describe different kinds of situations in a graph, particularly with discontinuities. We can also think of these in a more colloquial way if you want. So here are just some ways that we can describe these kinds of continuities in a more intuitive way. But again, this is just to help think about stuff, but we want to be able to use this notation when you're describing discontinuity. So we would kind of classify this first discontinuity as an infinite discontinuity. So just in looking at the first graph. We could call that an infinite discontinuity for obvious reasons, right? It just goes up to infinity. There's no point there. In the second graph, some people will call this a jump discontinuity. Maybe it wouldn't be a bad idea to just put these in quotes here, because again, we don't really want to use these, but it's okay to talk about them this way sometimes. Number 3, I don't really have a word for this. I guess you could call it a hole discontinuity. I think that may be the best way to talk about that. A hole discontinuity. And these are kind of the only 3 types that we'll really encounter. So why don't we take a look at a larger graph and determine where some discontinuities are. So this is a crazy function. Take some time to pause this and maybe sketch this graph to the best of your ability here. It's doing a lot of crazy stuff. It's got some vertical asymptotes. It's got a jump. It's got a hole. It's got a little crazy like wave thing going on. And it's just all over the place. So we're going to find and describe any points of discontinuity. So just locate the points where the function is discontinuous. And then we will also describe where the function is continuous. So kind of the same question, but just writing in slightly different ways. So you might want to pause this and see if you can just try to make a list of all of the x values. Okay, so points of discontinuity are all of the x values where the function is not continuous. So pause this and try to see if you can make a list. All right, I see just moving left to right. You can even take your pen and just kind of, okay, I'm going along, I don't have to pick up my pencil here. But then once I get to -2, that's a problem, right? We have a vertical asymptote. So -2 is a discontinuity. So let's start making a list here. Discontinuities. Okay, we have x equals -2. And if you want, we can label these. So this would be a vertical asymptote. We don't have to write the actual reasons here right now in terms of the limit notation, but it helps to kind of classify a little bit. So we call that a vertical asymptote. All right, going along down here, this is all nice and fine and continuous. We have this weird behavior here like this, but that's okay. I haven't had to pick up my pencil at all until we get to here. Right here we have a jump in the graph. So here we have another point of discontinuity. Here we've got a jump, so x equals 1. We've got a jump in the graph. All right, moving along here, we're just following after 1. We keep going, and it looks like right here, we've got another jump in the graph here at x equals 4. All right, so let's put that comma, x equals 4. And again, here we've got another jump. Okay, moving along, we're just kind of going along the function here, and this is nice and continuous until we get to 5. We have a vertical asymptote there. So this would be another point of discontinuity. Okay, so it's a vertical asymptote. Then after 5, we keep going along the function here, and it looks like at x equals 8, we've got another jump there. It's kind of small, but it is a jump nonetheless. So here's our last discontinuity. We call this another jump. Okay, so I know that this graph doesn't continue on, right? It stops at -5. It doesn't go beyond -5 here. There's no arrow. It doesn't go beyond 8, and that's okay. That doesn't mean that the function is not continuous because it doesn't continue on. It just stops there. Its domain in its entirety is from -5 to +8. Okay, so if we were going to kind of take this information and write it in a slightly different way to describe where the function is continuous, that would be everywhere else. So you don't have continuity necessarily. I mean, it is at a point, but it's at a bunch of points. So we want to describe this using intervals. Using interval notation. Okay, so as we are going along the graph, we have this, well, from -5 up to -2, we have some continuity there. There's a smooth piece. So -5 to -2. Now we're not going to include the -2, but we could say that there's a sense of continuity from this side at the -5 because it's filled in there. It's not like at the other end here where there is a discontinuity at the end point. So one way that we could describe this is including -5 in our interval, or it's continuous from one side, from the -5 side here. Or sorry, from the right side, right? So from this side here. Okay, then we're going to go from -2, okay, all the way up to 1. That's our next point of discontinuity. So we'll union -2 to 1. Now we had a discontinuity at 1, and it's not continuous from either side because the point filled in is up here. Okay, so neither one-sided limit actually meets the function value there. So we're going to exclude 1 in its entirety. So no open parentheses here. We'll also have an open parenthesis after 1 as well. Okay, then we have continuity going all the way to 4. Okay, but the function value meets the limit from the left-hand side here. So we have continuity on this side, so we could put a closed bracket here on the 4, as opposed to here, we go from 4 to 5 and we have a continuous part of the function. But we're not going to include 4 on this side of the interval because we're not including, there's a hole here. The limit from this side doesn't match the function value. So we'll say from 4 to 5. I know it looks weird, but it's a little more specific than just leaving out those including or the hard brackets there. Okay, then we have from 5 to 8. So we'll union 5 to 8. And then at the end point, at the 8, we don't have continuity at the actual value of 8. Right, there's this jump here. So we're not going to include 8, so we'll have an open parenthesis there. Okay, so we can extend this notion of continuity from one side or the other, if the limit from one side meets the function value, like in the case here, here, or over here. Okay, so here we included -5 from this side and 4 from this side. Okay, so to practice this, you have some questions on your written homework. A really cool fun graph to look at, and you also have some web-assigned questions too. So maybe if you want to go try just graphically determining continuity or just discontinuities, you might want to pause this and go check that out now. Otherwise, we are going to kind of try to figure out how to algebraically locate any points of discontinuity. Before we do that, though, I would like to give you some general guidelines or some general properties of continuity. Okay, so this is just going to summarize when certain kinds of functions are not continuous. General properties of continuity. The first general property is that all polynomials, so remember that is powers of x added and subtracted together, made with numbers in the front. They don't have any denominator with variables in the bottom. So, like lines are polynomials, quadratics are polynomials. That's the second degree. Cubics are polynomials, that's the third degree. Quartics are fourth degree, quintics are fifth degree. You could keep on going, just anything like that. They are what we would call well-behaved. And yes, this is actually a math term. Well-behaved is actually a math term. So this just means that they don't have any discontinuities. Right? If you think of the graph of a polynomial, they're just nice curves. There's no holes, there's no vertical asymptotes, there's no jumps, there's nothing crazy going on. They are very predictable and well-behaved. So they don't have any discontinuities. They are continuous everywhere. So you could say they are continuous on negative infinity to infinity for all real numbers. There are a few main functions that we will see in APM 105 that can have discontinuities. So I'm just going to summarize those for you here. So there are 3 main functions that can, I guess, in APM 105, there are more, but we won't talk about certain kinds of functions in this class. Kind of just keep it simple with polynomials and rational functions and piecewise functions and stuff. So there are 3 main functions in this class that can have discontinuities. The first is rational functions. So we've been looking at these a lot with limits. right? We've seen that these kinds of functions can have holes in them. These are things that look like a polynomial over a polynomial. So I'll write this as like p of x over q of x, or a polynomial that has x's in it over a polynomial that has x's in it. So these will have discontinuities whenever the denominator is 0, because those will result in a hole or a vertical asymptote. And so these are not going to be places of continuity. So wherever the denominator is equal to 0, or q of x is equal to 0. So this is really similar to domain. A lot of functions are only continuous on their domain. So in that vein, with continuity on the domain, root functions, even root functions, okay, these will have discontinuities wherever what's inside of the radical is negative. So these will be discontinuous wherever what's under the root or under the radical is negative or less than 0, right? Because we can't plug in negative numbers into an even root. So if that's going to, I mean, that gives you an undefined value. So there's not going to be really any part of the graph that's happening when you have this kind of thing happening in root functions. There's never going to be a part on the graph ever, no points at all, when you have a negative underneath. So that's the second kind of function. And the last one is piecewise functions. So these are the ones that have maybe 2 or more functions that are different for different parts of their domain. So these could have a break where the functions switch. Okay, so these could not meet up in the right way. So these could have discontinuities. Where the function switches. I'll put switches in quotes because I don't know how else to call it. But when it changes from one formula to the next, they could not be meeting up in the right way. Okay, so these 3 kinds of things are what we need to be looking out for unless we have a polynomial. In that case, the continuity will just be everywhere. There will be no discontinuities. All right, so let's take a look at some examples with finding points of discontinuity. In example 1, we have f of x equals x squared minus 16 divided by the square root of 2 minus 4. So on first glance, this looks like a rational function, right? It's got a denominator, there's some x's in there. However, the bottom actually doesn't have any variables in it. So what we have in the denominator here is actually just a number. And it's approximately negative 2.5858. And so if you wanted to, you could say, all right, this is approximately, so we use the squiggly equals for approximate, x squared minus 16 over negative 2.5858. And I mean, the denominator here will never be 0. So this is actually just a polynomial, like in hiding, it just looks like a rational function. The denominator is not actually a function of x, it's just a number. So this will just be the no discontinuities. Right, there's no root up top for us to worry about. And so there we are, no discontinuities for this. Okay, in example 2, we have g of x equals 2 divided by x squared plus 1. Now this is indeed a rational function. Okay, this is actually a rational function, right? We have x's, in the bottom. And if that's the case, then we are no longer a polynomial. We have a rational function on our hands. So we want to see where the denominator is equal to 0, and that's going to give us any places of discontinuity. Okay, so if we set the denominator equal to 0, this is going to give us x squared plus 1 equals 0. And we want to solve for x. Okay, so if we go ahead and it kind of looks like a difference of 2 squares, but it's actually a sum of 2 squares. These things never factor. A sum of 2 squares is not factorable. So if you want to go ahead and try to solve for x here, you could subtract 1 from both sides and then take the square root. You'd get plus and minus. We end up having to take the square root of a negative number, and this is imaginary, not real. And in this class, we're only concerned with real numbers. So no matter what x value you plug in here into the denominator, you're never going to get a 0 out. Just intuitively, that should make sense, because if you square a positive or a negative number, you're going to get a positive number. And then adding 1 will always make it positive, more positive. So there's no way that you will be able to get 0 out here. So again, this one has no discontinuities. Okay, so no asymptotes, no holes, or anything like that. In example 3, we have another rational function. This one's got x's up top and x's in the bottom. Okay, so this is again a rational function. And so we want to figure out where the denominator is equal to 0, because that's going to give us some discontinuities if it can happen. So we're going to set x squared minus 4 equal to 0 and solve for x. Okay, we can just ignore the numerator completely. It doesn't play any role in determining just straight up points of discontinuity. We are going to classify points of discontinuity in the next video. And in that case, we will consider the numerator. But in this case, when we're just finding all discontinuities, we just want to see where the denominator equals 0. So we've got x squared minus 4 equals 0. 2 ways to solve this. You could factor. This is a difference of 2 squares. So that'll factor into x plus 2, x minus 2. And so this will give us x equals negative 2 and x equals positive 2. Or if you like, what you could do is just set x squared equal to 4, or add 4 to both sides. Then when you take the square root, just remember that you have to take the plus and the minus, right? Because both positive 2 squared and negative 2 squared would give you 4. So I like the factoring method because sometimes we forget about taking the plus and minus when you apply square roots. But if that makes more sense to you, you can do that. Again, just make sure that you include the positive and the negative when you apply square root. So in either case, we are going to have 2 discontinuities. And they are going to be at x equals negative 2 and x equals positive 2. Okay, example number 4 is a lovely piecewise function. It is f of x equals 1 if x is less than 2. It's x plus 3 if x is between 2 and 4, and then equal to 7 if x is greater than 4. So I would say in this case, a graph is going to be a good way to figure out if this function is continuous. So luckily the pieces that it's made up of are relatively simple. So I think this might be also a good review just for practicing. So let's graph this. Now each part individually, the 1 and the x plus 3 and the 7, these are all polynomials. I know the 1 and the 7 don't look like it, but they're just constant polynomials with really boring ones. So individually, each of the parts won't have any issues. The only case that might, or the only point that we might have some problems at, or a jump in the graph if they're not meeting in the right way, is where the function switches. At 2, there's a switch, and then at 4, there's a switch. Okay, so let's see what happens when we graph this. So let's put our axes here. I know that x, I'm really focusing between 2 and 4, so I'm just going to put like, don't need too much of a negative axis for x. Okay, the line y equals 1, or f of x equals 1, so I'm just starting with this first part here. That's going to be for x less than 2. Okay, so let's just make, so we got 1, 2, 3, 4, 5, maybe 6. Okay, so for x less than 2, so that's going to be, you know, everything from here back. We're going to have the function y equals 1. Okay, so I'm just going to go up to 10 here. I'm not sure exactly what the y values are going to be, but this should be good. So y equals 1, the function y equals 1 is just a horizontal line. I'm putting an arrow this direction because it's forever that way. And then when we get to 2, we are not actually following this equation anymore. We're jumping to the next one. So when we get to 2, we're going to have an open circle down here on that point. Okay, so this is the equation y equals 1. All right, then between 2 and 4, we got the equation y equals x plus 3. Okay, so I know we know how to graph lines by using intercept and slope, but it might be better if we just plot some points here because we're only looking at a snippet of it, so it's kind of hard to see. So I'd say let's just make a little chart here. Let's say we've got 2, 3, and 4. So when we plug a 2 in, we're going to get 5. When we plug a 3 in, we'll get 6. When we plug a 4 in, we'll get 7. All right, so 2, 5 is going to be on our graph, and we're going to fill that circle in here. Because when x equals 2, we're up at this line. 3, 6, somewhere about here, and 4, 7, so that's somewhere about here. And so here is that point. And again, this is filled in here because when x equals 4, we are still on the line y equals x plus 3. So I'm just going to label that part. Okay, so this one's happening between 2 and 4. Then we have from 4 on. So now this one's going to look like y equals 7. Okay, so that's a horizontal line at the y value of 7. So let's see, 5, 6, 7. So that's here. That's the same point actually that this point is at, right? So that's just going to mean that this curve here is going to become a straight line like this, or a horizontal line. So there's that line. Okay, so just based on the graph, it looks like that at x equals 2, right, we've got this jump. The limit from the left and the limit from the right are not matching. Okay, so we have a discontinuity there. So let's note that. We definitely have a discontinuity there. Then at 4, right, at 4, these happens to be glued together in the right way. Right, the limit from the left and the right, they met up at the same point. So there's no discontinuity there. Okay, so this would be our only point of discontinuity. Okay, in the next video, we will distinguish between 2 different kinds of discontinuity. They're called removable and non-removable. So tune into that, and I'll see you then.